presentation?
Yes.
Great. Thanks for the opportunity to present here. Frank and I have had some interactions in the past and a lot of great exchanges of information. So glad to have this Tim to do it more formally. So thanks for the invite, Frank. We'll be talking today about our work in accelerating pilot training using physiological sensing, and all of this work is done in virtual reality. The big impetus for the program is that there's a huge shortfall of pilots in the Air Force. Recently reported about 2,000 pilots of a shortfall in the Air Force, and there's similar reports across the Navy and the Army as well. And the DoD is working across a number of ways to address these shortfalls, increasing the recruiting and retention of pilots, streamlining the logistics around pilot training to expedite that, learning management systems, and so on. So there's a lot of great work happening to address these issues. We're approaching this problem by aiming to accelerate the pilot training pipeline itself. This project is under a larger umbrella of work. So we're working with MIT campus. I myself am a technical staff at the MIT Lincoln Laboratory, and we're a federally funded R&D center. And we're working really closely with the Department of the Air Force, and we have airmen on this project as well. There are a number of really great projects going on under this umbrella, but this I'll be focusing on today is on predicting pilot performance and accelerating performance through physiological sensing. So let me step back as to why we think that physiological sensing could add value here. And we're going to borrow from some of the affective gaming and computing literature. The player gains the most from a particular challenge or a game by playing at when the difficulty of the game matches their level of competence. And in that case, they're in what's called this flow channel. But if the competence of the player far exceeds the difficulty of the game, they may not be challenged as much and reach some level of boredom. So this is inefficient training. And during this type of boredom, there are a number of physiological indicators that might tell us that they're in this state. Conversely, if the difficulty of the game is just too high compared to what the competence of the player is, well, we might see some converse physiological responses. And in the extreme cases, an individual may just stop trying because it's just too hard. So we believe that physiological data may add value to standard performance measures to, in turn, expedite the training progression. So what we'll talk about today is the VR environment that we've developed, as well as the multimodal data acquisition platform. How we have developed some sensor fusion algorithms to help predict this neurocognitive state and decline. This is very much ongoing work. And as well as our attempts at a open source data challenge, much like what Frank and team have done to make all this data public in the attempts to engage with the AI community. So let's first talk about the experimental setup. Here's a little bit of what it looks like. The tasks are happening in virtual reality, HTC Vive Pro Eye. We're using the X-Plane 11 flight simulation software, along with some of the same types of controllers that are used in the Air Force. And we have a suite of physiological sensing, by means of respiration, ECG, EMG, PPG, speech, body movements, and so on. And all of these data are time synchronized using an open platform called the lab streaming layer. And so lab streaming layer handles a lot of the round trip packet time, as well as timestamping each data that comes in with a common time frame. The experimental procedure that we use, it's called the instrument landing system, and we've liked adapting this type of a procedure for the VR environment because it's something that every pilot has to do. If you want to land a plane, you need to be able to follow the instrument landing procedure. And essentially what that is there are emitters, basically radio frequency emitters at the runway that give indication on the pilot's instruments how in line they are with the descent, as well as how well they're coming in at that -3 degree descent into the runway. The other reason we really like this from a research point of view is that it's extremely simple. It's required by all pilots. We can quantify the individual's performance at every time point by seeing how far away they're deviating from what's ideal. Um, and we can make it quantifiably more difficult, so we can titrate the difficulty by adding wind shear, changing visibility, adding turbulence, so momentary shifts in altitude. So taken together, this is extremely relevant for commercial and operational environments. It really tests the qualities of a good pilot, and from a research point of view, it has ways that we can make it quantifiably more difficult and continuously measure them an individual's performance. So I'll give you a sense of the highs and lows of difficulty. So on the left, you're seeing what an easy difficulty would look like. I'm guessing the video is coming in pretty choppy for you, but I'll just try to paint a picture with words. There's no turbulence, there's no wind. The pilot can see the runway the whole time, and it's kind of a straight shot down to the runway. The hardest difficulty, it's hard to see, but the person's moving the joystick quite a bit. There's really no visibility around. The plane's rocking everywhere because of wind shear and turbulence. And really you can't see anything, and the runway sort of comes out of nowhere, and they have to land right away. So this is as difficult as it gets. We had subjects do 4 levels of difficulty. With these are the ways that we made it harder. And each subject did 3 blocks of all 4 difficulties, with the difficulties being counterbalanced across the 3 different blocks. We measured performance using 3 independent measures. One is how well did they come in, straight and narrow down to the runway. This is measured in ILS lingo. It's called the localizer error. And ideally, they want to have 0 localizer error. We also measured their glide slope, or their descent down to the runway. And ideally, they wanted to keep a -3 descent angle. And we also measured their airspeed. For this particular aircraft, they had to maintain 115 knots. And we took these measures based on just real Air Force pilot training procedures and things that a student pilot would be graded on as well. So we thought that these were very realistic to how pilot training occurs. And all of these measures were computed instantaneously, as well as a cumulative measure for that trial, which is the sum of the absolute value of the errors of these components. So these are some representative example results of performance. And what you can see here is the difficulty level averaged across the 3 different blocks across novices and non-novice pilots. The first thing to take note is, especially for the non-novices, those who have had prior experience with flight simulators or flying generally, we see that as the difficulty increases, we see steady increase in the amount of flight error, meaning they do worse for harder difficulties. But novices, those whose first time it was in this, doing any kind of flying in this flight simulator, show a lot more erratic behavior, and generally everything was challenging for them. And what was also nice and reassuring to see is, subject E, who was a Air Force pilot, so very experienced, also had this type of graded performance for this difficulty. So it has a pretty high ceiling for maxing out someone's capability. This was just validation for us to say, hey, our difficulty that we put in as experimenters is indeed generating the type of effects that we want to see, and we're able to really striate an individual's performance across difficulty and across subjects. Happy to take questions as we go along too. If I'm going fast through it, or if people have questions, feel free to stop me. There are a couple ways that we've really thought about the results, but something that I'm really interested in is the eye tracking, and let me talk about that a little bit as well. Before getting into the eye tracking results, what we first did was talk to instructor pilots. So we interviewed several of them across multiple different Air Force bases. And we didn't talk specifically about eye tracking initially. I just asked questions like, what, as instructor pilots, what would you want to have access to make you better instructors? How can you better train student population are you missing? I try to keep it broad, high level to say, what are some of the biggest gaps currently in instructing students, and what tools do you need to do your job better? One common thread that we saw across a lot of instructors is them saying that they really needed to understand and note where the students were looking, because where the students are looking gives you really keen insight into what they're thinking. So if they haven't looked at the stage in a while, it kind of means that they haven't thought about it. Or if they're looking at the instruments, or if they're looking outside the cockpit, it tells you what information they're trying to access. In a VR environment, the instructors don't currently see where the student is looking. And in a real cockpit, they sit front back, and so they can't see what the students are looking at. So overall, they thought that this was extremely important, but a big gap currently in pilot training. So we thought then about what this means for us in our experimental scenario. And early in the run, especially when there's not a whole lot of visibility out, we expected that students, or all of these subjects would look more instruments and not really focus out. There's no information to be had by looking outside the cockpit, and to line up the plane using the instruments. In the middle of the flight, especially in some of the middle difficulties like 2 or 3, where they come from under the clouds and can start to see the runway, we expected that they may use the horizon to help align their plane to the runway, but still the runway is really, and they would likely gain the most benefit from focusing mostly on the instruments. And finally, just before touchdown, we would expect that they should primarily just look at the runway itself. You could look at the instruments if you land the plane on the runway, and if you can see the runway, you might as well use it. So we realized that instructor pilots really wanted to know where the students were looking. We built a hypothesis based on our experimental design, what we expected students to do. And now to acquire the data, the eye tracking data, we use the HTC Pro Eye. I know that there have been some really great demonstrations, and Frank and I have talked at length about the eye tracking in the Pro Eye, and NASA has really good capabilities. But just to give you a sense of what this might look like, here's a movie demonstrating what a single person's gaze looks like in time. And so when they're looking down at the instruments, you can see that their gaze intersects at this lower point. But when they're looking out of the cockpit, really there's no gaze intersection, and they're just looking out at infinity, or optical infinity. So what we could do is detect when they're looking outside versus when they're looking inside the cockpit and at instruments. And we use this information to gather the fraction of time they spent looking outside the cockpit versus inside the cockpit. At first, the thing that stands out the most here is for the easier difficulty to spend more time looking outside the cockpit. And as the difficulty gets harder because of less visibility, they spend more time looking inside the cockpit. And that makes a lot of sense. Use the information you have available to you. And the non-novices exhibited a lot more of a stereotype behavior than the novices. But we broke this down by time and aligned the time to the landing, basically. So the end point here is when they land, and stepping back in time means that they're further away from the runway. And you see that across the board, subjects initially spend more time looking inside the cockpit, but as they get closer to the runway, spend more time looking outside the cockpit at the runway. But at higher task difficulties, when they're presumably a lot more cognitively loaded and having a much more challenging go of things, what we see is a distinction in behavior between novices and non-novices, that the non-novices immediately switch over to say, if I can see the runway, I'm going to use it. But novices think that, hey, this is an instrument landing system task. I need to look at the instruments. That's what's going to give me the information. And they exhibit a slightly different suboptimal behavior. What this tells us is that this eye tracking data can actually provide very actionable insights that can be given to the instructor pilot to say, guide the behavioral change, figure out what they're doing wrong and help them start to mimic more expert behavior this way. Really, we don't want to just have the student in the loop with the AI. What we want to do is have the system help to guide both the students and the instructors and kind of have it all be in a loop. So that's a little bit of insight into the eye tracking data. There's a whole lot of other sensory modalities that we haven't been able to touch on here, but let me talk a little bit about the data challenge that we posed and how we made all this data public and how you might have access to the data as well. So we posed the problem as, hey, there's a big pilot shortage and we need to be able to train pilots faster, just as I posed the problem here today. And what we did was we collected all of this data. And at this point, we have about 35 subjects worth of data. And this ranges from novices to extremely veteran Air Force pilots in terms of expertise. And we collected all of that physiological data, including heart rate, eye movement, head movement, body movement, accelerometry, respiration rate, muscle activity of the joystick hand, all of the user interaction, all of the flight performance behavior, and everything like that. So I won't belabor this too much because we already talked about the experimental paradigm, but the challenge that we really posed to the AI community was, can you predict performance just from the physiology? I know you have access to some of the flight movement performance measures, but we really wanted to say, what is in the physiology that helps us infer the person's cognitive state? And can we add to the standard performance metrics of the flight performance insights gained from the person's physiology and their cognitive state? So we executed this data challenge and we had a great turnout. This was in partnership with the Air Force Chief Data Office. And we had about 109 participants, which broke down into about 20 to 22 teams or so. About 7 teams completed the challenge and submitted their code. And we had some really great insights gained from all of that. So if anybody is interested in getting access to all of this data, please let me know. We have it all open source and we'd love to help you, take on this challenge. So this is really important work that we think that we're doing, and we see a lot of value to not just the Air Force but across the Navy and Army as well. Pilot training is ubiquitous across the DoD, and VR is becoming more and more relevant. As I don't need to tell anybody here on this call. We really see 3 potential ways that we can bring this technology out and transition it to the end users. There's some really great software that is being adopted across the Air Force. Cloud Ahoy, which is a debrief software. So you can put in things like all your flight data and it gives you insights into different phases of your flight, the movements, and so on. And we've worked a little bit with Cloud Ahoy to try and include a new set of variables called human factors. And these human factors can include things like heart rate, standard measures of physiology, but they can also include more complex measures such as your derivation of cognitive load. And you can align that data to the flight maneuvers and what's happening in real time. Sorry, you can align it post hoc, but you can play back as a debrief tool. Developing great 3D tools to represent eye tracking on the instruments. I think this is still an important thing here. Frank and team showed a nice simulation in 3D at the start of today's call, and I think there's still room for growth in actually implementing this into pilot training, having the students and pilots, instructors gain information from it, and actually using this to improve pilot training. I think the technology is there. I think we need to focus on the transition and integrating this, into the actual process. And lastly, I don't want to call out any company specifically, but there's a lot of really great industry partners that are building technology that is, airworthy, and can be put into cockpits to measure physiology. There's a lot of great good that can be done by assessing someone's physiology, especially detecting when someone's going, into a physiological episode or something's not right, and alerting the pilot or the co-pilot. So I think transition into industry is something that we should really consider as well.
It's also
just to
no matter how strong he makes the security there,
was there a question or a live mic?
From got a live mic. Let me see who it is, and I'll try and mute him.
Okay, I think they got it. Yeah. Just wrapping up though. We started this project because there was an important shortfall in pilot training, and we thought that among the other solutions the DoD is using, we thought that physiological sensing can add value to cognitive state estimation and prediction of pilot performance. VR is a really great way to deploy this. VR is very operationally relevant for training, and provides a great test bed for us to deploy these types of technologies and algorithms. We're collecting a lot of data, and we're going to continue to collect data through this year to have around 50 to 60 subjects worth of data. Each session is about 4 hours worth of physiological data and flight performance. So we're happy to make this all open to you so that you can apply your algorithms and take it and publish and so on. And we really think transition is key here, and we want to make sure that what we do gets out of the lab and into the hands of the end users. So we look forward to partnering with everyone on this call, industry and so on, to make sure that what we develop here makes it out into into use. We have a wonderful team. I'm just the lucky person that gets to talk about what's happening here. But we have professors at MIT, graduate students at MIT, members of the Air Force that help really guide all of this. Gouge McAlpin is a pilot and has really helped drive a lot of this. Oh, hey, Kyle's on the call. Thanks. We have a lot of really great folk at MIT as well. So please let me know if you'd like to connect and continue discussing with all of this. And happy to take your questions. So I think Gouge addressed the question about centrifuges. We don't have that at the moment, but.
Yes, this is Joe Schmidt again. I'm a former or retired Air Force flight surgeon, and you really have incredible research going on here. People do get motion sickness in simulators. That's an interesting use case. And then also, if you put this into a G centrifuge and to see the changes that happen in the pilot scan would be very, very interesting, as well as, when people before they start feeling motion sick or responding to the Gs, this will be something else to see. And then also the active feedback, if someone does not notice something, say a target that went by the screen or a sensor that they didn't notice, and then the machine can give them direct feedback. So really good work. Over.
Thank you, sir. I really appreciate the feedback. And I think with the centrifuge, I think predictive analytics is really the name of the game, right? To predict when they're going to do G-lock, or what types of physiological signals can help us get 5 seconds, 2 seconds in advance of when that happens would still be beneficial.
All right, any other questions from anybody around the loop? All right, doesn't sound like it. So thank you for the great presentation, Kesh. I found our conversations over the last several years very fruitful, and hoping we can continue to have those. Again, with that said, thank you very much.
Thanks, Frank, and thanks to the team, and have really enjoyed all the presentations that I've seen today. So thanks.
All right, so let's see, who do we have